if you can
We can
hear
hear you.
me clearly.
Yeah, we can hear you.
Okay, thank you so much. Thank you for confirming that.
Absolutely.
Yeah. Okay. Good morning, everyone. I want to welcome you to my lecture today. Of course, the material for today, of course, has already been published on the course canvas, but I'm going to use the board throughout today, reviewing the material, for today. We started the last chapter. Before I'm going to go to before the last chapter, let me just tell you this: the final exam will be cumulative, and the final exam will focus on chapter 2, chapter 3, chapter 4, chapter 5. Oh, sorry, 2, 3, 4, 5, 6. There's not going to be chapter 1 because the chapter 1 is too elementary. But let me just tell you the distribution. Chapter 2 and chapter 3 will be 40%. Chapter 4, 5, 6, 60%. There will be 5 questions in the final, and each question will come from one question will come from chapter 2, another one from chapter 3, 4, 5, 6, like that. But in terms of weight, chapter 2 and chapter 3 will be 40%, and chapter 4, 5, 6 will be 60%. Does that make sense? So that is the way it's going to be. So I'm going to release practice questions this week. Of course, we've just started the last chapter of the semester. Okay, so let me just write what I have for you today. Okay, so today, actually, we started function of random variable. Okay, we're actually seeking a distribution of the function of random variable. So distribution, okay, of the function of random variable. So today, I'm actually going to focus on two methods of figuring out the distribution of the function of random variable. Yesterday, we focused on the method of distribution function. Okay, I started the method of moment generating function, but I didn't finish that. Okay, I'm actually going to revisit that method of moment generating function. Okay, and method of transformation. Okay, these are the two methods that I basically want to focus on today. Of course, let me quickly have a recap on what we're trying to achieve. We got a particular random variable that follow a particular distribution, and we got a new variable that can be expressed as a function of the old variable, and we basically want to, we're seeking to figure out the probability distribution of the new variable, putting into consideration the probability distribution of the old variable. Of course, I've walked you through that. We got different kind of methods that we can actually use to figure that guy out. Number one is the method of distribution function. I think I walked you through that yesterday. And another method is the method of moment generating function. And another one is the method of transformation. So what I want to do now, I want to start with the method of moment generating function. But I will advise that if you want to talk about method of moment generating function, you need to be able to get yourself familiar with the moment generating function of random variable that follow a particular distribution. You need to know that. Okay, let's have a recap on them. If I'm talking about Bernoulli distribution, where x, x follow Bernoulli with parameter p, okay, and the f of x is a p raised to power x 1 minus p raised to power this s start from 0 1. Okay, I derive the moment generating function to be q plus pet. Okay, I derived this yesterday, so you need to be able to get yourself familiar with the moment generating function. And of course, yesterday, okay, and I said, okay, if I have a random variable, let's say x, and x equal x1 plus x2 until I get to xn, okay, and each of these is such a way that xi actually follow Bernoulli with parameter p, okay, Bernoulli with parameter p, okay, and I said the moment generating function for that now is basically going to be this guy here. Okay, of course, the approach that was actually used is that the moment generating function of each of these will have to be multiplied. Okay, and of course, if this is the moment generating function for Bernoulli, then this can actually be recognized as a moment generating function for binomial. So which means the moment I arrive at this, my conclusion is just going to be, okay, x, then followed by norm with parameter np, okay, and f of s is going to be n combination s, p raised to power x 1 minus p raised to power that s start from 0 1 2 until you get to n. We just deduce that. Okay, so now another one that I actually want to talk about, uh the moment generating function for Poisson distribution. If I have Poisson distribution, x follow poi, let's say with parameter lambda, where f of x equal exponential raised to power lambda raised to power s over x factorial, s start from 0 1 2 all the way to infinity. Okay, if that is what I have, okay, the moment generating function is expected value of e raised to power ts, so which is going to be this guy, okay, the f of x, x start from 0 to infinity. Okay, to infinity. Okay, so summation x start from 0 to infinity e raised to power ts exponential raised to power this lambda raised to power x over x factorial. If you take a look at that, okay, if you take a look at that, so why am I doing all this? You need to know the moment, just like, okay, you need to know the state capital of state in the United States if you want to make an inference about United States. Okay, so here now, exponential raised to power this, okay, s start from 0 to infinity. I can combine this guy and this guy, so which is going to be e raised to power t lambda, everything raised to power x divided by x factorial. If you take a look at that guy now, okay, the mx of t now equal this. Okay, you remember the Taylor series here, right? Okay, you can on all of these, that is the same thing as exponential, okay, raised to power this. Okay, so if I combine this guy now, I'm actually going to be having this minus this, which is basically lambda into this minus 1. So anywhere in the world, this is a moment generating function. for Poisson distribution. Okay, I've given you that of Bernoulli binomial. Okay, you have that of the Poisson right now. Okay, now I've given you that of a normal. Okay, please take note of take note of that. Okay, give me 1 second. I believe those of you online, you can see the board, right? Those of you online.
Yeah, we're able to see and hear.
Okay, thank you so much. Okay, so I'm gonna go into normal. Okay, I derived that yesterday. If x follow normal with parameter mu sigma squared, where f of x is 1 over square root of 2 pi sigma squared, and this is what we have. Okay, where the state space is actually between that and that. Okay, yesterday I derived the moment generating function. Okay, I derived the moment generating function. Okay, for normal mx of t to be equal exponential raised to power mu t plus sigma squared t squared over 2. Okay, I derived that yesterday for normal. Okay, now based on this, now I quickly want to do something. Let's say we have random variable y, okay, which is equal to or let me say we have a random variable x. Let's say we have or u. Let's say we have random variable u, which is x1 plus x2 up to xn. Okay, and if you take a look at this and you are told that xi follow normal with mu I sigma I squared, okay, which means x1 follow normal with the mean. The mean is going to be mu1. The variance is going to be sigma 1 squared. Now, we now want to figure out what is the distribution of u. Okay, the question is, what is f of u? Okay, but you already know the f of x to follow normal. Okay, what is going to be f of u? Of course, you know that expected value of u is going to be expected value of x1. We know all of that. Okay, which is the expectation of summation xi. I start from that, and that is basically going to be summation. I start from that, the expected value of si. Okay, and that is basically going to be n. You actually since they are not the same, so you basically going to have summation. I start from 1 to n mu I. Okay, and of course the variance of u, if x1 up to xn are independent, right? Okay, of course we've already done that before. Okay, all the way to xn, okay, is also going to be the sum, okay, of the variances. Okay, now if I want to use the idea of the moment generating function, if I want to use the idea of the moment generating function, okay, if I want to use the idea of the moment generating function, maybe I want to find mu of t. And don't forget, what is u? U is x1 plus x2 until you get to xn of t. Okay, and you know that this guy is the same thing as expectation of t into x1 plus x2 until you get to xn, which is going to be the same thing as this t x1 expected value tx2 until you get an expected value txn, and where this become the moment generating function for that, the moment generating function until you get to what I have here. And of course, the moment generating function of a normal distribution to be this guy. Okay, so all what I'm just going to do, here I'm actually going to write mu1 t plus sigma 1 squared t squared over 2. Okay, for this, e mu 2t plus sigma squared over 2 until you get to this guy here. Okay, now when you combine this guy now, okay, you're basically going to see that you are going to have mu1 plus mu2 until you get to mu n, okay, t, then plus, okay, when you take a look at this guy 2, you're actually going to have sigma 1, sigma 1 squared or sigma 2 squared until you get to sigma squared n, okay, t squared divided by 2. Look at that. So if I want to generalize this guy now, I'm actually going to have summation mu I start from 1 to n, okay, this t here, I can put that here, plus, okay, uh, summation, or maybe I first put a constant out, I put t squared over 2, right? Okay, so I put t squared over 2, then summation sigma I squared, I start from 1 to n. Now, I need you to focus now, okay, this. If this guy is the moment generating function of a random variable x that follow normal distribution, then this guy is the moment generating function of a random variable u that is a sum of x1 up to xn, and each of them distributed according to normal. So when you take a look at what you see here, what does it mean here? Summation mu I. What does it mean here? What does it mean here? Mu, right? What does it mean here? Look at t. Look at t. What is the mu here? Summation mu I. What is the variance here? Sigma square, right? Okay. The variance, you're like you have a t square over 2, the sigma square. Okay. T square over 2, this is the variance, which is this guy here. Okay. So this is the moment I see something like this, okay, I know the moment generated version of a normal, and they told me that each of this is distributed according to normal distribution, and I want to obtain the distribution of u, okay, and I go by way of moment generating function. The moment I have this, I will just compare this with the existing moment generating function of that, and I can conclude the distribution from here. Okay, so what I'm going to tell the world now, what I'm basically going to tell the world, okay, so what I'm basically going to tell the world is that, okay, when you're talking about you, then you follow normal with the mean, okay, mu I start from 1 to n, and mu and sigma this, I start from 1, I'm done. So this become the distribution of u right now. Do you know we can also have a situation? Let's say what of if u is a1 x1, a2 x2 until you get to an xn, where we have a linear combination, okay, based on this. And of course, you're told xi follow normal with mu I or sigma I squared, okay, then we want to find the f of u, okay. In this situation, if I want to find the f of u, if you take a look at here, I can go by way of moment generating function, okay, which is going to be, okay, so here now, what I can do is, okay, what is I'm seeking to get the moment generating function of that. of AISI, because each of these is AISI. Okay. Now, if I get the, so let me for even though I want to get this the moment generating function of the sum, I want to get the moment generating function of the sum of of that. But let me first talk about the moment generating function of a particular linear combination before I even go to that of the sum. Okay. Now, when you see something like that, okay, when you see something like that, you first what you're going to do first is, if I have uh let me first, so that I don't confuse you. uh Let me first, this is what we want to find, but let's first consider this guy. Okay, we want to consider MAIXI. What does that mean? That can be written as XI into AT. Okay, if that can be written as SI into AT, okay, then what are we talking about? Okay, uh if uh if XI, okay, if XI follow normal with mu I sigma I squared, the moment generating function of that is e raised to power mu I t plus sigma I squared t squared over 2. We know that this exists for this. Now, I want to find this guy now. So I'm gonna say M A I X I T equal, where here AT, wherever I see T, I'm just gonna plug in AT. Take a look at that. Wherever I see T, I'm plugging in AT. Okay, let's see. So which is gonna be, okay, AIT plus sigma I squared. Okay, when by the time I plug that in here, does that make sense? If this is a moment generated function, therefore this is going to be this. Now, the moment I know this guy now, I can now come to obtain the moment generated function of u of t, which is, now I'm seeking the one for the summation. Okay, I'm seeking the one for the summation right now. Okay, and what is going to happen is, this guy, the same way that you plug in a t on t here, I can plug in the whole of the summation. So what am I going to have is basically going to be summation mu I a I, okay, t, okay, plus t squared over 2 summation I start from that ai squared sigma I squared. I'm done. Okay, so which means the mean and variance here is different from the mean and variance here. The mean here is mu I, okay, ai. The variance here is sigma I squared ai squared, but the mean here is a sum. It included that. This is the mean here, okay, and the variance here is this guy here. Okay, we've used the method. So if I now want to write the distribution for this, just like the same way I did for this guy now, just like the same way I did here, I'm actually going to say that you follow normal. What does it mean? Summation mu I a I, where I start from 1 to n, and the variance summation a I squared sigma I squared I start from 1 to n. This is the distribution. Okay, and that is the idea. Now, there's another distribution that I want to derive the moment generating function apart from normal. The method I've been using so far is a method of generating function, right? Okay, now I want to talk about gamma distribution. Okay, I want to talk about gamma distribution now. Okay, now if x, let me for first, let me write gamma distribution. If x follow gamma with parameter alpha beta, the f of x is basically s raised to power this exponential raised to power this gamma alpha beta raised to power alpha this this this. Of course, I've walked you through a gamma distribution. Okay, now what is the moment generating function? Because if you are given a random variable u that is equal to x1 plus x2 up to xn, and if each of them is distributed according to gamma, and they wanted to use the method of moment generating function to figure out the distribution for you need to first know the distribution of the gamma. Does that make sense? Now, you need to first know the moment generating function of the gamma. So the moment generating function of the gamma, expected value of this is going to be integral. The range is going to go from 0 to infinity, e raised to power tx, f of x dx. Okay, f of x dx. Those of you online, can you still see my whiteboard, right?
Yep, we're good.
Okay, thank you so much. In case you are not seeing it, please let me know. Okay, now the ms of t equal 0 to infinity e raised to power tx, x raised to power this exponential raised to power this divided by gamma alpha beta raised to power alpha dx. What am I doing now? I want to derive the moment generated function of a gamma distribution. Okay, now if you take a look at this is a constant, 0 to infinity. I can combine this guy and this guy. I'm actually going to have tx minus that dx. If you combine that, okay, now when you take a look at this guy now, I can rewrite this as this 0 to infinity x this exponential right here, oh sorry, ts minus that. I have this, so if I factorize, that's going to be x, as s is going to come out. Okay, t minus 1 over beta dx. Okay, if you take a look at that, and if I put over 1, I can rewrite this as 1 over gamma alpha beta raised to power alpha 0 to infinity s raised to power that exponential raised to power x into if I have this. Okay, so I'm actually going to have beta t minus 1 dx. Okay, now if that is what I have, okay, I can actually I can rewrite that guy as, if I have mx of t equal 1 over gamma alpha beta raised to power alpha 0 to infinity, I can write out x raised to power alpha minus 1 exponential. Okay, if I put a negative x, if I put a negative, that is going to be this 1 minus, right? Any question up to this moment? Any question? You're fine, right? Okay, so I can use the method of substitution, okay, which is going to be, right, y equal to that, because I really want to use a gamma function. But before using gamma function, I need to tidy it up. Okay, this implies x equal to what? Beta y over 1 minus beta t. Okay, so what is going to be the y dx? The y dx is 1 over this, and this implies dx equal beta dy over 1 minus beta t. Yep, beta dy. Now, if I want to rewrite this guy now, I'm actually going to have 1 over gamma alpha, this 0 to infinity instead of x. I'm actually going to put this raised to power alpha minus 1 exponential raised to power this instead of dx. Instead of dx, I'm actually going to put this 1 minus that. Okay, that's where we are now, right? Any question? That's where we are now. Okay, now the next thing that I want to do is, so the next thing that I actually want to do is, if I have mx of t equal 1 over gamma alpha beta raised to power alpha 0 to infinity. Okay, here beta raised to power alpha minus 1, y raised to power alpha minus 1 divided by 1 minus beta t raised to power alpha minus 1. So I simplify that. Then I got exponential raised to power this beta, the y divided by 1 minus beta t. Okay, take a look at this guy, this guy, this guy. They're basically going to cancel out. Okay, they're going to cancel out. You see that? And when they cancel out, if you take a look at this guy and this guy, okay, so basically I'm going to have 1 over 1 minus beta t raised to power alpha 0 to infinity, y raised to power this, exponential raised to power this, the y. Okay, can somebody tell me? If I want to use a gamma function, okay, uh, if I want to use, okay, don't forget there's a gamma alpha here, right? There's a gamma alpha here. Okay, if I want to use a gamma function, what is this? That's a gamma alpha, right? This is a gamma alpha. If you want to, this is something as gamma alpha. So it's going to be gamma alpha divided by gamma alpha 1 minus beta t raised to power alpha mx of t. So this cancel this. What do I have now? 1 minus beta t raised to power negative that. Anywhere in the world, this is a moment generating function of a gamma distribution. And don't forget, if this is a moment generating function of a gamma distribution, okay, I can say that I can deduce the moment generating function of a chi-square distribution from that. You remember chi-square, right? You remember chi-square distribution? When alpha equal to v over 2 and beta equal to 2, we have a chi-square, right? Now, if x now follow chi-square with a degree of freedom v, okay, with a degree of freedom v, okay, where f of x is basically going to be x raised to power v over 2 minus 1 exponential raised to power minus x over 2 divided by 2 raised to power v over 2 gamma v over 2. This is a chi-squared density. All I just did is to plug in this for alpha and b for 2 in a gamma. Then I can deduce the moment generating function for a chi-squared. I'm just going to come here. Okay, I'm also going to plug in alpha to be this, beta to be that here. Okay, I'm going to say 1 minus, okay, 2 c, okay, raised to power minus instead of alpha v over 2. Look at this. This is a moment generating function of a chi-square. Don't forget, a relationship exists between a chi-square distribution and a gamma distribution. If I know the moment generating function of a gamma distribution, I automatically I can deduce the moment generating function of a chi-squared. All I'm just going to do is to plug in alpha to be v over 2 and b equal to 2. I'm done. Okay. So if a question is now asked about the moment generating function of a gamma to be this, and you basically have a random variable that follow a gamma distribution. Okay, maybe you are actually maybe maybe you are giving maybe they gave you u to be x1 plus x2 until you get to xn, and you are told that xi follow gamma, okay, with parameter. You know, at times you could have random variable that follow a particular distribution and they all have the same parameter of truth. If they have the same parameter of truth and you basically want to figure out the moment generating function of that, which is this until you get to xn for t, and don't forget, I told you it's just going to be the product, right? It's just going to be the product, right? The product, if it is the product, and you already know the moment generating function for gamma to be that, so which means I'm actually going to have this, okay? I'm going to have this until, by the time at the end of the day, this is going to, you see that? You see? And this is a situation where each of these have the same alpha and beta. But what if in a situation where it is not like that, where they have their separate, okay? What if in a situation if where they have their own separate, if they have their separate, let's say for instance, you're told that xi follow gamma, okay, with alpha I, beta I. Here it is the same for all of them, but here it is different. So if you want to come here, okay, the moment generating function in that regard, okay, don't forget, like I said, x1t, x2t, until you get to xnt. In that situation, okay, here you're going to be this raised to power minus alpha 1, okay, 1 minus beta 2, t, okay, raised to power alpha 2, okay, that will continue to go. So in that situation, or it's going to continue to go to 1 minus beta n t, okay, raised to power alpha n. This is the general one. Okay. Now in this kind of situation, okay, I'm afraid writing that in a general form may basically be this guy. Does that make sense? In that kind of situation where they got different, because it's going to be a product. Okay. Now this is using the method of moment generating function. Okay, all the way. I think what I'm going to do, because we're meeting today, we're also meeting on Monday. What I'm going to do today, I will focus mainly on, let me see. I can start. I think I still have time. So this is how the method of moment generating function work. Is there any question before I go to method of transformation? Before I go to method of transformation, is there any question? Okay. The next thing that I want to talk about now is the method of transformation. In the method of transformation, we have Jacobian, we make use of Jacobian transformation. Okay, so how do we use the method of transformation? I'm actually going to walk you through now for discrete and for continuous. Okay, so we want to talk about method of transformation. Okay, for the method of transformation, I'm going to talk about one variable situation, and I'm going to talk about two variable situation. Okay, and I'm going to talk about this for both discrete and continuous. Okay, for the method of transformation. Now, let's see how the method of transformation actually work. Um, I'm going to start from the continuous aspect today. Okay, take a look at this. We solved a problem yesterday in class. Okay, we solved a problem yesterday in class using the method of distribution function. Okay, I'm going to remind you of what we did. You're giving f of, okay, I want to start example now. You're giving f of y to be equal to 2y, and the range of y is between this, and of course they want you to find f of u so that you will be able to find the expectation and the variance as well. Okay, we know we use the method of distribution function yesterday, and by the time we use the method of distribution function, let me remind you of what we got. We actually got 2 into u plus 1 over 9 as the f of u. Now, on this same problem, I want to use the method of transformation. Okay? On this same problem, you know, when we started yesterday for the method of distribution function, we first of all get the CDF. After getting the CDF, what we do? We differentiate the CDF. We arrive at here. But right now, I want to walk you through the method of transformation. But this is for one variable. You can see here, variable y, variable u. That's one to one. I want to start for one variable situation. Okay. Then the complicated one is going to be two variable, but I want to start from one variable now. Okay. If I want to start from one variable now, what I'm going to do is, if I want to use a method of transformation for continuous, I need to first get, if u equal to this, then I need to first get the inverse of that. So what is y? So y will be equal to what? Y is going to be u plus 1 over 3. You remember yesterday we did something like that too, right? Under the distribution function. Okay. Now, if y equal to this, then I need Jacobian. Okay. What is the Jacobian? Is basically going to be the y du here. The y du. Okay. What is the y du now? The y du is 1 over 3. Okay. Then you need to find the absolute value of Jacobian. We don't want negative. We don't want negative. We want a positive, right? Now, we got this guy now. Then I'm going to come back here. You know, f of y equal to 2y, right? Then I need to, you know, my f of u, my f of u is going to be f of y, okay, which as a function of that multiplied by determinant of Jacobian. So what I'm going to do now is I'm going to write 2 instead of y. What is y? U plus 1 over 3. What is the multiplied by determinant of Jacobian? So what do I have now? 2 into u plus 1. Okay, 3 times 3, 9. I'm done. I'm done. Method of transformation is easy. Method of transformation is very, very easy. Look at that. And you need to determine the state space of y, of u. The state space of y is 0 to 1. Okay, if I plug in 0 here, that will be negative 1. Okay, so you here lie between negative 1. If you plug in 1, okay, that would be 3 minus, that would be 2, right? If you want to know whether you are right, all what you just need to do is to integrate that over the range of -1 to 2 if he give you one that is correct. Because if this guy is wrong, if this guy is wrong, this guy will be wrong. Because if you want to get the expected value of u, you're basically going to say u, f of u du, okay, -1 to 2. You are using that f of u. Do you know that? Can somebody remind me if I don't want to, let's say for instance, if you're given this, we are coming into that because they asked you to find f of u. Let's say they did not ask about this and they only ask about this. If they don't ask about this, that would be super easy. You know what you're going to do? Look at this, right? I'm going to show you something now. If you're giving u to be 3y minus 1, if they ask you to find the expected value of u, you remember what you did before? 3 expected value of y, you remember? And you can just make use of this, the y over the range. You see that? If you plug in what you get here, is it going to give you the same results? You know what I'm trying to tell you now? If you use the f of u here and you find the expectation of u, you will get the same result with what you're going to get after when you get this and plug this here. But why are we going through all what we're going through now? Because we want to figure out the distribution for you. That's why we're going through all of that. Does that make sense? Okay, this is 1 to 1. Okay, for 2 to 2, I'm just going to write that and I'm going to continue tomorrow. Okay, I just walk you through the one variable. Okay, for two variable. Okay, particularly we have it. There's a distribution in statistics called T, and if we have if T equal z divided by this, okay, where z follow normal, standardized normal, okay, where f of z is 1 over square root of 2 pi this, okay, z lie between -infinity and infinity, and w here follow chi-squared, which is f of w, okay, where w raised to power r over 2 minus 1, the divided the exponential is power w over 2, okay, gamma r over 2, 2 raised to power r over 2, okay. There are two variables here. That's why each of them have a distribution, okay. You now want to derive t, okay. This is like 2, the way it's looking now, 2 to 1, but we can never have 2 to 1. We're going to have 2 to 2. So what I'm going to do, I'm going to create an artificial variable, okay. That very k is going to be equal to the variable in the denominator. It's going to be equal to w, okay. So which means I want to go from zw to tk, and after getting the joint for the tk, I will integrate out this guy. I'm going to show you this tomorrow, the final result. The final result is the t distribution that you all know. The final result is this guy is going to be f of t equal gamma r plus 1 over 2 divided by square root of this gamma r over 2, 1 plus t squared over r raised to power that. This is the end result. I'm going to show you tomorrow, where t lies between -infinity and infinity, okay. This is the t distribution. This is the origin of the t distribution that you use in statistical analysis, to figure out the p-value for t-test. Lastly, I want to give you another example. This time around, for f distribution, I'm going to derive that for you tomorrow. F distribution, Okay. F equal u divided by r1 v divided by r2. U follow chi squared with r1, v follow chi squared with r2. Okay. Now this follow chi squared, that follow chi squared, and your h of f at the end of the day is going to be f r1 over 2 minus 1 r over that's going to have r1 over 2 divided by b into r1 over 2 r2 over 2 then into 1 plus r1 r2 f raised to power minus r1 plus r2 over 2. Okay, so I'm also going to derive how we arrive at this tomorrow, but I'm just trying to give you an example of a 2 by 2. Okay, the idea of a Jacobian transformation is basically going to be used. Okay, so you don't need to be scared. I'm going to walk you through all this, So, do you have any question before I go today? It's already the time. Any question? Like I said, there's going to be 5 questions in the final. Okay, a question is going to come from chapter 2, chapter 3, chapter 4, chapter 5, and 6. Chapter 1 will not be tested in the final. Because chapter 1 to me, it looks too elementary. And of course, I'm going to release a practice question. So I'm going to meet you tomorrow. Today's Wednesday, right? Yeah, I'm going to meet you on Thursday. I'm going to meet you on Monday. Okay? We're going to finish the class on Monday, and uh, then there's going to be on Tuesday, maybe for practice questions. Then I'm going to review that with you, and you're all going to be good. Okay, expect your midterm two results this week. We've started grading, like I said. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.